So, Hess's law. This is weird. It's mathy, but it's weird. And the reason it's weird is because it's like putting together a puzzle and simultaneously solving in math class. You remember when, I think it was algebra, you would have like two equations and you could substitute, or you could graph, and where they intersected was the answer, or you did simultaneously solving. That's what this is. So what Hess said is, because energy is a state function, which means that the only thing that's important is where you start and where you finish, and how you get there doesn't matter. So because of that, you can go through one step to make a chemical reaction happen, or you can go through a million steps. As long as you can get from the beginning to the end, the path doesn't matter. And then remember, we said that enthalpy is just a fancy word for heat. So when we have a chemical reaction, we either have to figure out, is it exothermic or endothermic? Did it absorb energy or did it release energy? And that's what the enthalpy change is. During the reaction, the enthalpy change is given as delta H. And Hess says that we can do this in one step, or we can do it in a bunch of steps. Your hand warmer experiment, you could have done math and figured out how much the enthalpy change was, because Q equals MC delta T. You could have found the mass of the water, you could have found the specific heat of the water, you knew a temperature change, but you have to calculate to find heat. And what we did wasn't toxic, you dumped everything down the drain. What if you want to do a new reaction that is toxic? Somebody's already done those experiments. And there's lists of them everywhere. So maybe it's not exactly your experiment, but maybe they did parts of the chemicals that you're going to use in your experiment. So you can manipulate what they did and figure out what you're trying to figure out. And that's what Hess's law allows us to do. So you're going to be given a reaction, and they're going to say, what is the enthalpy change for this reaction?
Landon, Clausen, and Cole Underwood, please report to the
edit.
attendance office.
That's for posterity now, because I don't edit. Okay, so you're going to be given reference equations. And so you're going to take these reference equations and you're going to try to make the equation that you want to make. And sometimes you might have to flip them around because you need something to be a reactant and it's a product. Or maybe you need two of something and it's only one of something. So you have to multiply by 2. So that's where the rules come from. If you have to reverse a reaction to use it, you have to change the sign on the enthalpy. So negative enthalpy changes means exothermic. So you make it positive. Now it's endothermic if you have to flip the equation. If you need 2 of something, you have to multiply through by 2 for the equation, then you've got to multiply the heat by 2. And we always use delta H. And when I give you problems to do in this class, because this is the first year chemistry class, you're going to be given the equations that you need to use. When you go to college, they might give you a whole bunch of equations. Some of them you'll use, some you won't use, but we're not going to do that. I'm going to give you the equations that you need to build the equation that you're looking for. And I'm going to do 4 examples with you, and then you're going to do a bunch, and these aren't due until Thursday. And there's one of these, no there's not, there's 2 of these on the test. One's super easy, one's slightly harder, and then there's one that's a bonus that's super hard. But it's a bonus. I'm gonna do a bunch, you're gonna do a bunch. Your second period class, and not this for posterity, they don't talk very much, but I could tell that the people who enjoy math, they sort of like this. They liked it when it all worked out, and then there were other people that weren't quite so happy. So I don't know, we'll see how this goes. I like these, I think it's like building a puzzle, it's like figuring out a puzzle. Sometimes the delta H's, like we just been using delta H by itself, but if you notice on the hand warmer lab that you did, it said the delta H of solution, or they used to put this, but I don't think they put SOL anymore because SOL. But the subscripts tell you what's going on, that's also for posterity. Anyway, they'll put reaction if it's a chemical reaction. They'll put F for fusion, which means like you're making ice cubes. They just put these weird subscripts. So you can do this for anything. You can do it for phase changes, you can do it for making solutions, you can do it for chemical reactions, but there's going to be energy changes for all of these different things. So we're just going to use delta H for right now, but if you decide that you're going to go into chemistry, you're going to have other chemistry classes that are harder. There's going to be all kind of subscripts involved, and I don't want that to be surprising to you. So what we're gonna do, and then I'm gonna turn off the camera, is I'm gonna do some examples. Hess's law. These are my examples. You can take a picture if you want to, or you can go on YouTube and look at them here once I get good Wi-Fi. I'm gonna do 3 of these on this worksheet with you and 1 on the worksheet that I'm giving you because it's super hard. They get a little bit harder as we go on in the problems. So the problems are always worded like this, and I don't know if the camera can see through me. Probably not. So I'm gonna move a little and find paper. So this says calculate delta H. So that's the energy, the heat. They want to know the heat change for this reaction. And the reaction is C2H4 plus hydrogen makes C2H6. We can't do that in here. I don't have the facilities to do that, but this is the equation I'm trying to make. We do not balance this. That's not the point of this. We're trying to find the amount of heat needed to make exactly 1 mole of C2H6. That's what, I don't know what it is. That's what I'm looking for. I'm trying to figure out, is it exothermic? Is it endothermic? What's going on? So these are my 3 reference equations that somebody has done these experiments. Somebody has taken C2H4 and burned it in oxygen and it made carbon dioxide and water. And they, like you did your lab and you figured out how much the temperature changed, they did the same thing. They figured out that this reaction is exothermic and it gives off 1411 kilojoules of energy for every 1 mole of C2H4 that's burned. That's why we don't balance. I'll get to that in a minute. Somebody else did this experiment. Notice the fractions. That's the other thing people don't like, but it is what it is. I know I told you that coefficients could never be fractions. Yes, they can, when you're talking about energy changes. So to burn 1 mole of C2H6, you need 7/2 of a molecule, which of course is not possible, but this is just math, and it makes this, and it's exothermic and makes 1560. And then hydrogen gas and oxygen gas come together to make water. And the fractions are there, and we keep the fractions there. We don't balance anything. What we're trying to do is use these 3 equations to make this equation, because Hess said, I don't have to do this all in 1 step. I can go through 3 steps, or 4 steps, or 12 steps to get to this. Now, this is what I do. I label these A, B, and C. Not everybody does that. This makes it easier for me. You do not have to do this. And then I look at the equation I'm trying to make out of these 3 equations. And I go to the very first thing, C2H4. And I look for C2H4 in my reference equations. So here's C2H4. It's not anywhere else. It's not anywhere else. It's just here. So in the reference equation, it's in, I'm calling this A, it's a reactant. Well, I need it to be a reactant, so that's fine. There's an understood 1 in front of it. There's an understood 1 here. It's perfectly fine. So I'm going to use this entire equation with its energy change to help build the reaction that I'm looking for. So I'm going to use A as is. So I put down A, and then I write it. C2H4 plus 3 O2s. And I leave out the states of matter, but sometimes they're hard. Sometimes they'll have liquid water and gaseous water, but I'm not going to give you one like that. And then there's 2 CO2s. I write it just as it is because I didn't have to change anything. And I put its enthalpy change over here, negative 1411 kilojoules. You can put kilojoules per mole if you want to, or you can just put kilojoules. That's the amount of energy that it liberates when it burns 1 mole. Okay, so that took care of the C2H4. It's in the right spot with the right number in front of it. Then I go to the hydrogen. Okay, and I look for hydrogen. There's hydrogen here. There's hydrogen here. Is there hydrogen anywhere else? No. So I'm going to use C. Okay, how am I going to use C? Well, I need hydrogen to be a reactant. Hydrogen is a reactant. I need it to have a 1 in front of it. It does have a 1 in front of it. So I'm going to use C as is. So I write C, H2 plus 1/2 O2. I don't make these decimals. I guess you could if you wanted to. And then the hydrogen, or the enthalpy change, is going to be exactly as it is, negative 285.8 kilojoules. Okay, that took care of the hydrogen. Now I go to the C2H6. Okay, where's the C2H6? By a process of elimination, I have to use B. Okie dokie. C2H6, up here, the equation I'm trying to make, is a product. In the reference equation, it's a reactant, so I have to flip it. Now, to let myself know that I have to flip it, I call it negative B. I'm using B, but I'm flipping it. So then I flip it. I put 2 CO2s plus 3 waters. Oh, and the number's the same, right? 1 here and a 1 there, so I don't have to do anything to that. 3 waters, and that's gonna make C2H6 plus 7 halves oxygen. And I flipped it, okay? So when I get to the enthalpy change, I gotta change the sign. That's what that rule was on the PowerPoint. So I used B, but I flipped it, so I have to change the sign. So this becomes a positive 1560. And I know in math world, positives are understood, and it is here too, but I just do this so that I know that I've changed it, that I had done the thing I was supposed to do. You don't have to do that if you don't want to. Now here's the deal. If I can add these 3 equations together, and they make this equation, then I can add these together, and that's the answer. That's what Hess said. If I can go through these 3 steps and make this equation out of it, then I can just add these 3 numbers together, and that's the delta H. So I have to think of the arrow like an equal sign and what I learned in math class. So C2H4, it's just in one place. But here's oxygen. So I have 3 oxygens and a half an oxygen on the left-hand side of the equation. So that's 7 halves, isn't it? 3 is 6 halves, and there's another half. So I have 7 halves oxygens as reactants. Well, I have 7 halves over here. They cancel out. It's just like math class. It's just like simultaneously solving, and things on the left side of the equation and the right side of the equation, they can cancel out. So 3 oxygen is 6 halves oxygen, plus another half of an oxygen means I have 7 halves on this side. There's 7 halves as products, they cancel out. Okay, let's see what else I need to have cancel out. There's no CO2 up here. There's 2 CO2s as products, there's 2 CO2s as reactants, they cancel out. There's 2 waters plus 1 water is 3 waters. There's 3 waters over here as reactants, they cancel out. And then I say there's nothing else to cancel out, I put everything back together. So I've got C2H4 plus hydrogen. There's no other reactants left, everything else canceled out, and C2H6. I made it. And since it worked, I add these 3 up, and that's my answer. Because Hess said I can do that. So negative 1411 minus 285.8 plus 1560 is, that's not the right answer, what am I doing? 1411, negative 1411 minus 285.8 plus 1560 is negative 136.8, and that's kilojoules. So this reaction, I don't have to do it, it's exothermic, it's negative, and for every mole of C2H4 that reacts with the hydrogen, it'll produce 137-ish kilojoules of energy. We're gonna do more, not on camera, but we'll do more.
There'll be no editing.